All right, let's jump right in. When I say the word math, what's the first thing that pops into your head? For a lot of people, it's, scary calculations, maybe even a little bit of stress. But what if I told you math isn't just about crunching numbers? What if it's actually a language, a really powerful, elegant language that's designed to describe the very world we live in?
The great astronomer Galileo Galilei definitely thought so. And this quote, it really hits the nail on the head for what we're talking about today. The core idea is that mathematics is this universal language that helps us see and talk about the world around us. It's not so much about memorizing formulas, it's more about becoming fluent in a totally new way of thinking.
So, how do we get fluent in this new language? Well, here's our game plan. First, we'll look at why it's so universal. Then, we'll get into its alphabet and grammar, the difference between just a phrase and a full sentence. We'll cover the really important rules everyone agrees to follow, have our very first conversation using something called sets, and then we'll wrap it all up by looking at why this language is so crucial for understanding reality itself.
Right, so unlike, say, English or Mandarin, the language of math is pretty much the same no matter where you go on Earth. The statement 5 + 5 = 10 is a solid truth, whether you're in Cairo, Tokyo, or Buenos Aires. The symbol 10 means the exact same thing to everybody. It's this incredible shared foundation that makes it such a powerful tool for science and collaboration all over the world.
Every language needs its alphabet, right? It needs words. Math is no different. Its words are all the symbols and little notations that have been developed over thousands of years, all to express ideas with total clarity and speed. And you'd be surprised how far back this stuff goes.
Yeah, this is not a new invention, not by a long shot. Humans have been building this symbolic language for thousands of years. From the hieroglyphs in ancient Egypt to the number systems of the Sumerians, we've always been looking for ways to write down these abstract ideas about quantity. That ancient history is baked right into the language we use today.
Today, the modern alphabet of math is built on the digits 0 through 9. And its vocabulary? Well, that's all the operators and symbols, like plus, minus, equals, greater than, less than, you get the idea. These are the words that let us build ideas. So instead of having to write out the sum of 2 and 3, we can just, poof, write 2 + 3. So much simpler.
Now, because of these symbols, the language of math basically has 3 superpowers. First, it is incredibly precise. There's no wiggle room for interpretation. Second, it's super concise. You can pack huge, complex ideas into just a tiny bit of space. And third, it is unbelievably powerful. It lets us talk about complex relationships that would honestly take pages and pages to describe in a regular spoken language.
Okay, so we've got our alphabet, we've got our words, but just throwing words around isn't really communicating, is it? We need grammar. And in math, that means really getting the difference between a simple phrase and a complete sentence.
Let's think about it this way. A mathematical expression, like 3x + 2, it's just a phrase. It's like saying a blue car. It's an object, but it's not a complete thought. You can't say a blue car is true or false, right? But a mathematical sentence, like 3x + 2 = 11, that makes a full claim. It's like saying the blue car costs $11. Now we've got a complete idea that we can actually test. We can figure out if it's true or if it's false.
For any language to actually work, everyone using it has to agree on some basic rules. You can think of them like conventions. They're the shared grammar, the etiquette that makes sure we're all speaking the same language and not just causing total chaos.
A perfect example of this is the order of operations. A lot of us learned it as PEMDAS. Now, this isn't some deep law of the universe. It's just a convention we've all agreed to follow. It's what makes sure that everyone, everywhere, solves 2 + 3 × 4 the same way. We all get 14, instead of some people getting 20. Without these agreed-upon rules, communication would just completely fall apart. Here's another really important convention. Math loves to borrow words from everyday English, but it gives them these super specific technical meanings. So you might talk about a group of your friends, but in math, a group is a very particular thing with its own definition. And the same goes for words like ring, field, and factor. That level of precision is absolutely essential.
And these conventions get so detailed, they even control how the language looks when you write it down. We all agree to use italics for variables, for example, or bold for vectors. This shared visual grammar means a mathematician in Japan can pick up a paper written by someone in Brazil and immediately understand it, even if they don't speak a single word of the same spoken language. It's amazing.
Okay, theory is great and all, but the best way to learn any language is to actually start speaking it.
Usually, one of the first things you learn is how to talk about groups of things. You know, these books, those people, us. Well, in math, that's the language of sets. It's really the most fundamental dialect. So let's use it to have our first conversation.
The whole idea of a set, which was really pioneered by a mathematician named George Cantor, is beautifully simple. A set is just a collection of objects. That's it. And these objects, which we call elements, can be anything at all: numbers, people, letters, even other sets. The only catch is that the collection has to be well-defined, which just means we can always clearly tell if something belongs in the set or not.
So there are two main ways to write down what's in a set. The first one is called the roster method, which is kind of like calling roll in class. You just list every single element. So here, set A is the collection of A, E, I, O, and U. Simple enough. The other way is the rule method, where you describe the elements by their shared property. So here we'd say A is the set of all things X such that X is a vowel. Two different ways of writing it, but they both describe the exact same collection.
And once we have our sets, we need some verbs to talk about how they interact. For example, a union just smooshes two sets together. It's everything from set A or set B. An intersection, on the other hand, only shows you what the two sets have in common, the elements that are in both A and B. And the subset just tells us if one whole set fits completely inside another one. These are the basic words for having a conversation with sets.
So we've gone over the alphabet, the grammar, and even a basic dialect of math. But why? Why go through all this trouble? Why does learning this strange, symbolic language actually matter in the real world?
It all comes down to one crucial word: abstraction. Math lets us strip away all the messy, irrelevant details and just focus on the core structure of a problem. Think about it. The exact same math can describe how a funny video goes viral, how the interest on your bank account grows, or how a disease spreads. By unifying all these different situations under one abstract idea, we create these incredibly powerful tools for understanding how the world works.
And really, that's the big takeaway here. Math is so much more than just arithmetic. It is a language specifically designed to be precise, concise, and powerful. It's the ultimate toolkit we have for thinking clearly, spotting patterns, and communicating the deep truths about our universe. Which leaves us with one final big question to chew on. If we really accept that math is the language of the universe, this language of patterns and structures and relationships, then what messages are written out there for us? In the stars, in our own DNA, in the world all around us, just waiting for us to get fluent enough to finally read them. What is the universe trying to tell us?